ATMs and safes. And just a little disclaimer, for educational purposes only, please don't go around hacking ATMs or safes. For background for us, we work at a pen test company doing all different types of pen test engagements, web, network, mobile devices, wireless communications, hardware, red team, SCADA stuff. What we're going to go over today is just ATM safe overview, some historical attacks, some devices that we analyzed and their security implications, some wireless analysis, mobile application analysis, some hardware analysis, and some of the vulnerabilities and mitigations. So for a lot of electronic equipment and also security equipment, there's an organization called Underwriters Laboratories, and they certify a lot of these devices. And for safes, especially like commercial safes, ATMs, electronic equipment, high security equipment, they certify a lot of these things. They have a standard right here, 687, that governs what a solid construction of a burglar-resistant safe looks like. And tool-resistant, TL, is a rating that they say, TL 15 minutes of tool time that a professional burglar would take to get into a safe. Torch-resistant means they take a blowtorch to it. And explosive, TX resistance, means they would strap explosives to the safe and try to get it out. And they have different ratings of 15 minutes, 30 minutes, and X6, or in 60 minutes. And also X6 means all 6 sides of the safe. They generally will test the front of the safe, and if you have an X6, then they'll test all 6 sides. So an example would be TR-TL30, a torch-resistant, tool-resistant safe up to 30 minutes. And TX-TL60X6 would be something like explosive-resistant, torch-resistant, and tool-resistant for up to 60 minutes on all 6 sides. So we got a little vid here for you. So this video right here is the Underwriters Laboratory testing a safe using a torch. You can see. So he's trying to generate a hole, and the idea is that if you create a hole a certain amount of distance of width, and if that happens, then your safe fails. The certification isn't qualified as a They'll also use, after they take the blowtorch to it, a jackhammer-like tool to knock out some of the melted steel or concrete that's in between it as well. And for these TLTR type devices that are certified for burglary resistant, they also stipulate that you have to have a UL Group 1, basically mechanical lock on it, or a Group 1R, basically high security and also X-ray resistant, and 2M, manipulation resistant, and Type 1. Type 1 is for electronic type locks. It's the highest security that you can do. So they're standard for burglary resistant mechanical dials. Group 1 would be 20 hours of manipulation resistance. They have like 3 experts that try to manipulate the lock, and if you're unfamiliar with this technique, essentially they rotate all the wheels, try to figure out how many wheels are in the lock, and they calculate the contact points on the lock, and then they try to figure out the distances and then map them, graph them, and then after that figure out the combinations. And then, as I said, the 1R, radiological attack resistance, if you were to take an X-ray. 2M, 2 hours of manipulation resistance, and then Group 2, which is what you'll see most, home safes and safes in stores and stuff like that, moderate level of resistant, level of resistance. For electronic locks, they have a different certification. Type 1 says 30 hours of unauthorized access to the lock. And Type 1 devices are used to protect classified materials and also high-value narcotic stores and or art objects and military purposes. And you typically see like a Type 2 for like banks and stuff like that, jewelry stores. Type 3, more like commercial facilities, and Type 4 for a lot of other lower security applications. So they do a bunch of testing for the electronic locks. A lot of it has to deal with safety testing. They do some security testing, applying high voltage, low voltage current, and jarring attacks. You might have seen some safes that are small you can buy at Walmart. You can just drop them on the ground and they'll just pop open. Some historical attacks, like a punch attack. Essentially, you either create a hole or use the hole that the mechanism has, and you punch out the back the lock body of it, and as it pops out, you can basically open the safe. Auto dialing, automatically dialing all combinations or a subset of combinations, and manipulation, I discussed that earlier. Drilling, a lot of people, safe technicians will drill into a lock and then figure out the combination by using a camera or like a reset button on an electronic lock. Vibration attack, where you essentially shake the safe or device until the wheel pack like aligns to the proper alignment. X-ray or C4, which is a fun one to explode the device. You also see some people strapping their car and some change to an ATM and dragging it away. Skimmers, those are particular to like ATMs. You'll see skimmers where you put in your credit card or ATM card and it'll read out the PIN number and track it for the bad guy. They also do video cameras to capture the key pins when you enter it. And then microphones, so they know they can link the sound to the video of which buttons you're actually pressing on it. This right here is an auto dialer, and it was created by a guy we work with back when he was at MIT. And it's S&G created to protect high security containers. And essentially, to pull the bolt, you have to push the lever in. That's what you see kind of making this little clicking right here. So that's an example of an auto dialer. And this is the device that we reviewed. This is the device that we analyzed right here. You can see the front, that's the keypad device, and we hooked it up to that same guy in the video's safe. He was pretty happy about that. And here is an example of the original lock body on the back. And as you can see here, you actually see the mechanism right here. Also the wheel pack there. And here's what happens after we install the electronic lock on it. And you can see the bolt, when it gets pulled, you can unlock the safe. And for this particular lock, it has multiple users. It has a manager user and regular users. And the manager can do multiple things like reset codes. The user can just open the lock. It has a 6-digit combination, so 1,000 possible combinations, or 6-digit codes, 1,000 possible combinations. And you can add users. So big one, right? Default combinations. Gotta love that, right? The manager code, all ones. The user code, 1, 2, 3, 4, 5, 6. You can imagine in a typical installation, one code might be changed, no codes might be changed. A lot of people like keeping a default. The recovery code, too. You can enter that, and it'll give you back a random number, or quote-unquote random, and then you give it to the company, and the company will tell you what your PIN is. So the stipulation on that is you have to be a certified locksmith to do it. So you can see the back of the lock body here. There's a reset button as well. So a typical attack that maybe a technician would do if all else fails would be to drill the lock and then to use a small piece of metal to push that little reset button, and you would unplug the battery, plug the battery back in, and it would sync back up with the keypad, and you'd be able to open the safe. So this lock also provides Bluetooth as well, in particular Bluetooth low energy. And those who are unfamiliar with Bluetooth, think of regular Bluetooth as like headphones transmitting more data, and Bluetooth low energy as like a wearable device that transmits sporadically to save power. And this Ubertooth 1 is a device sold by Mike Osman and the same guy who created the HackRF, and it's able to analyze Bluetooth traffic. So here's kind of what a Bluetooth packet looks like from the lock here. You see that the first packet that you'll see consistently running from any type of BLE device, and this one in particular, is an advertisement packet, just telling you what the device is. I'm the lock, and it's basically saying it's Quintic pass-through. It gives it the BLE address and a couple other flags. And then here, the next request is a scan request. You're essentially asking for more information from the lock. And it sends back a couple different things. It sends back services and characteristics, essentially, what functions you can do. Can you read from a service or characteristic? Can you write? Can you do both? Or can you be notified when something happens? And based on this information, we can calculate certain unique aspects of the Bluetooth safe lock. And if we know what the ATM communication looks like, then we can do ATM war driving. So we can basically take a high gain antenna and figure out where these ATM safes are in the vicinity. So while using the tool, the Ubertooth 1, we ran into a couple issues. One issue that I thought was kind of funny was a nice stack smash, most likely buffer overflow here that's essentially overriding the stack cookie on the stack there and creating a core dump. That was interesting. There's also some other issues with getting advertisement packets and scan packets and actually receiving a connect request. In Bluetooth Low Energy, what happens is you scan request, or you listen for the advertisement, you scan request, get a scan response, and then after that, you connect, and on the connect, it gives you parameters. And the parameters that you really need are the particular time intervals and what distance to jump, because Bluetooth Low Energy will hops a certain sequence. So with those things, you can sniff it, and you need to be able to, you really want to sniff the data, right? So what we tried next was Texas Instruments CC2540, and it worked. It was great. And this is an example right here of a unlock request. And now that we know where the safe is and when it's open, well, we could go in and execute a physical attack if we really wanted to. So here's an example again of an unlock request for 123456, the 6-digit PIN from the mobile application. And you notice that the top request here says FFFFF5A5A. This is always static. It's just indicating that it's going to do an unlock. And then the next packet includes some other data. And if I send the same request with the same mobile device, the request looks like this. So can you guys tell the difference between the two? Right? So the only difference here is that the CRC and the RSSI change, and the CRC is just a checksum, and the RSSI is just the power level. So essentially, when I unlock the lock twice, it's replaying the same data. So that means that we can do a replay attack against it by capturing it. So after we knew this, we wanted to dig into the mobile application further to see if we can decode the packet, what's in the packet, stuff like that. And if you look at the download on Google Play Store, you'll notice it has a 1.0 rating, and it just says, needs work. So what is the mobile application store? Because a lot of times when you're analyzing mobile applications, it's important to see what it stores on your device. And it can give you other information about the security of the device as well. And in this case, you see it stores the voltage, it stores the lock state, open or close, and also how many seconds it's going to be opened, the Bluetooth addresses, and a couple other information. So looking around further into the BLE code of the mobile application, you see that it performs an unlock here. And the thing that's necessary for the unlock is the open second, the BLE MAC address, the open code, and then a couple other static variables. Oh, and the open code being the PIN that you type in. So you want to go? Sure.
So if we can go back a slide, you can see that when it saves the code, it parses it from the Android app as a string and converts it to a long int. And so we know that, okay, what we're dealing with on the Bluetooth packet is possibly a long int that might be encoded or encrypted in some way. And so we had to dig in a bit deeper. And you can see there's a send command here. And if you analyze the send command, it eventually goes into this compose function. And it looks a little obfuscated, I guess you would say. But once we broke it down, we found out that literally what it does is it takes this long int that was originally a string from the Bluetooth input activity and then writes it in reverse order into a Bluetooth packet and then sends it out. And the funny thing was, if you search around the code a little bit more, you could see that there's also an equal compose function that uses encryption or encrypt that just isn't used. So after we found this out, we went out and tested it, and we have this demo video. Got it.
Okay, so what's going on here is we have the smart RF Bluetooth packet capture on the left, a Python script that's listening, and the mobile application shown on the screen that we're using too. And as you can see, we're just capturing advertisement packets right now, and those are the green packets here. And in a second, we're going to open the app. And right now, you may see a scan request and response when it opened the app to figure out that it's what type of device it is that you want to connect to. Now we've connected to the device. You see the channel hopping here in the yellow packet scrolling. We're going to enter the PIN 654321 and then hit unlock on it. And you can see we've captured the password, and the safe is open from using the mobile application. Yeah, and you can see on the top right the Python script has basically showed the manager password there. 654321. Actually, can you guys see that? There we go. And now we got the money, so that's fine.
So after doing a wireless and a mobile analysis, we decided to dig in a little bit deeper and start looking at the hardware. And we feel like any good hardware analysis starts with a good teardown, because when you do a teardown, you can take high-resolution photos and identify each of the chips, which really helps with hardware reversing, so you don't have to keep going back with a magnifying glass and looking at all the chips again. And so here you can see that we have the entry pad and the entry pad back. This circuit board correlates to that entry pad. Then they're separated by a long cable, 4-pin cable, that connects to this board, which is the lock body circuit board. And this lock body circuit board, once it receives a command, charges this stepper motor, and that stepper motor is what actually pulls a bolt.
So another thing that we may not have said is we actually bought 2 devices, 2 of the same keypads and 2 lock bodies, one of which was Type 1 certified electronic lock.
So this is the entry pad board. The front of it has an LCD screen. Most of this is uninteresting, other than like it's a 9-volt input. The system is a 3.3 volt system. And then there's also additional 5-volt lines, if you look for it, that mostly deal with data protocol stuff like communication with the other circuit board. The back side of it is a little more interesting. We could see there's the power circuit here. This header connects to the keypad matrix. To the front where you actually enter in the keys. There's the backlock communication cable here. And you can also see that there are a few traces that are not populated with chips, which we speculate is probably because they use the same board for multiple different types of locks, or these chips were used during debugging purposes or development, and they were removed later on. But the most interesting stuff here is these 2 microcontroller chips, the main one being a Renesas, or formerly NEC 78K microcontroller, and then the Bluetooth chip at the bottom, which is an NXP 9020 Bluetooth system on chip. And so what happens here is the Bluetooth chip communicates with the mobile device, and then typically sends that data over to the main microcontroller, the Renesas, and they usually communicate over a UART protocol in most cases. The backside, or the lock body circuit board, is powered 5 volts over the communication cable, that 4-pin communication cable located here. And this also uses a Renesas chip, but a different model, the F9234. There's also some interesting stuff here. There's a debugging port, which the other board has as well. There's also another data port, which is interesting, and possibly a power connection. for powering it separately without a lock body. And then the reset buttons here. This is the lock body itself, obviously with the stepper motor. And once the stepper motor is powered, it pushes the bolt. Cool. So this brought us to our next attack vector, which being the most trivial. We thought if we have access to the entry pad, because it's very easy, when you come up to the safe, you're able to take off the entry pad so you can replace a battery on it, and you can take off the plastic casing. It'd be really easy to create some sort of electronic device that would basically sniff on the keypad, and then you can hide it. And since the keypad is a simple matrix circuit, basically you have rows and columns for the keypad, and the top columns or the rows are held to ground while the others are inputs to the microcontroller. So anytime you press something, a line is driven to ground, and then that's what the MCU registers as a key press. So this is how we tested it. It was with a multimeter. We just tapped a line and then compared it to ground with a voltage difference. And as you can see, there's a lot of empty space in the keypad, the entry pad. So you can probably attach something onto these lines here and then hide it underneath and put the back pad or back cover on, and then it'd just be incognito. And then you could have it just saving data or sending it back over the air. So this is what it measures when a key is not pressed, and then when you depress a key, it pulls to ground, and that's what the device would pretty much do. After doing that, we decided to look at the data communication between the entry pad and the back lock, the lock body. And to do that, it would basically be signal analysis, and we used a Cellier logic analyzer, which is supposedly the logic analyzer you'll love to use. It's pretty awesome. A logic analyzer basically allows you to attach onto pins on an electronic board and then record the digital and analog signals, and then you can record it and then analyze it later, apply analysis tools so it can decode protocols, and you can script stuff. It's pretty cool. We also use a dedicated power supply, because you should always use a dedicated power supply. Keeps things at a steady voltage, allows you to prevent overcurrent and stuff like that. And then a multimeter for your bread and butter to make sure there's continuity testing and stuff like that. So this is basically how we tested or did signal analysis. We took the 4-pin cable and we took a razor blade and we just skinned it a little bit and then tapped the lines and hooked it up to the Cellier. And after looking at it, we were able to deduce that's a 2-wire 8-bit protocol, 1 wire being clock and the second wire being both data in and out. Logical high is 5 volts, logical low is 0 volts. And when a communication starts, before it starts, both lines start high, and then clock drops, and then data follows right afterwards, and then transmission starts. So the top image would be a command packet, and the bottom image is the data packet. They vary in size, but they always start with a 0x byte and end with a 03 byte. And so the data in between, the payload can change in size, but it's always going to be in bytes. This is an unlock attempt with a correct pin, meaning that we typed in a correct pin and it unlocked the lock body in the back. You could see that there are 3 repeated command packets. They're exactly identical. And then there's a clock toggle. After the clock toggle, the line drops low, and then there's a unique data packet. And so this is an unlock attempt with a correct pin. What do you think an unlock attempt with an incorrect pin looks like? Nothing. So something's missing here. And it kind of drives a question, where do you think the security logic is stored? I mean, if you were to design a lock, you would think that you would do the security logic at the back lock. The entry pad would be dumb and just send the pins over to the back lock, and the back lock would do all that logic to determine whether it needs to be opened or not. But this is not the case. So signal analysis allowed us to analyze the communication behavior between the 2 modules, allowed us to even go in and compare different packets and extract pin data, and then also replay signals using an Arduino Mega, which was really cool. We were able to take a Salier capture and then export it, and then Marcus wrote a really clever Python script that would convert it into Arduino code, and then we'd just be able to replay it, which was pretty neat. Which led us to the question, why not create a brute forcer? And with making a brute forcer, we had to know like the pin states before and after transmission, the unlock packet, that clock toggle was very important, and then the unique data bytes in each packet that we would be brute forcing. And timing is also an interesting thing, because if you can cut up timing, you can optimize it and make brute forcing a lot faster.
So this right here, we're demonstrating that the lock is closed and just the normal operation of how the keypad and lock body works. You can see we just opened it normally with particular code, and now we're going to use a different code, all fours for this one. And in this case, the light turns red here. We have it hooked up. It's cool to show red instead of pull the bolt. So now we're going to disconnect the device and hook up our own little device to do a little brute forcing on it. And inside this black case is an Arduino that we've programmed to do a little brute forcing. And you can see that the device says there, type 1 high security. And it's open. And so, and now we're going to show on the other device with a different pin that we can also brute force this one as well. So you plug it in, you hit the power on, and boom, red light, it's open. That's it. This one? Yeah, sure. So basically an overview of the vulnerabilities that we discovered here. The ATM safe war driving poses some problems here. If you can find ATMs, all throughout the facilities, or even, if it's a type 1 device or, a high security device, a type 2, 3, 4 even, if you can identify where it's at, particularly in a building, you know where the money's at, where the valuables are, and you can potentially attack it. So it poses issues. The BLE sniffing, if we can know when a device is unlocked, and that poses issues that, a physical attack could occur when it's unlocked. I don't know of many burglaries that happen when they know when, or bank robberies that they know exactly when the vault door is going to be open or stuff like that. Pin disclosure too, we can sniff the pin and go back in, unlock the lock. Keypad sniffing too, so in this case we would pull off the keypad, plant a little malicious, hardware device, and then when the person went in and typed their key, we could also sniff that. And then also lock communication. We can also tap the other line that goes, that four-line cable that goes to the lock body. We can decode the communication, and then come back and replay that as well. And then also lock body brute forcing. We did a brute forcing here showing several combinations, but we still have a little bit more work to get all 1 million combinations. So for the mitigations here, BLE locks, Bluetooth locks is just, it creates a lot less security, and there's a lot of information you disclose over Bluetooth. So just be cautious, if you're buying these devices for, some type of installation, especially a high security installation. For protecting classified information, we recommend some of these electronic devices are, less secure than they probably should be. And an X10 is a better device, I would say, to protect against some of these type of attacks. The UL certification should probably add in new requirements. This is just our opinion. It seems that they do a lot of physical security testing really well. You saw that video with the torch and everything. And they do good testing for safety and some small electronic attacks, but they don't really look at the communication layer or anything like that. And there's not a whole lot of security standards that make these vendors, use encryption and all this kind of stuff to and from the keypad and the lock body and all these good things that we're used to. So special thanks to Mike for giving us some reverse engineering tips, Paul for taking some of the photos and filming the video, Grant for letting us use his device, tear it apart, and yet letting us use his safe too. And any questions? Yeah. Yeah, you do need to connect to the BLE device, but in this case, you don't need a pin. You know, there's no, if you're used to Bluetooth or Bluetooth Low Energy, typing in a pin to pair with the device, right? There's none of that. You just click connect and it sends. In terms of like Bluetooth security too, this is a good point. The question, if you didn't hear, was do you need a pair? And in terms of Bluetooth encryption and security at the protocol layer, you basically have a couple different encryption options. One is don't care, all zeros for encryption. The other is to use a PIN, but that as well has been known. There's public attacks against that where you can use a tool, I think it's called Crackle, to decrypt all BLE communications using that because there's only 1 million combinations. And then there's like a manual key mode where you can specify one key on one device and the other, and that's the most secure way to connect over BLE right now. The standards are coming out to do kind of a Diffie Hellman and more cryptographically secure stuff, but thanks for asking that. Yeah. Yeah, so on the lock body when you type in, so the question was, did you try any brute forcing with Bluetooth? And if you use the lock body, typically how it works is you only get 4 tries to enter a correct combination. And if you use the mobile app as well, or tried multiple connections, you only get, on the 4th try, you get locked out. And it has to wait for a certain amount of delay. Yeah, any other questions? Yeah, you here.
So how difficult would it be to get access to the lock control board from outside the safe?
So the question was, how difficult would it be to get to the lock control board? And there's 2 devices here in question. One is the keypad board, and the other is the lock body. The lock body is inside the safe, and there's usually a small hole that the cable goes through, and it's trivial to get access to the keypad. You lift it off, and you've got full access right there. Yeah, you've got access to the cable. You can plug that little thing in. Exactly. Now, and the keypad too, it's easy to install stuff on the front or mutate it or change it or whatever. It just pops right off. Also, it's not made of a very sturdy, steel or anything like that. You could drill into it or, pry it off with a crowbar. But on the inside of the safe where the lock body is or the ATM, it'd be harder to get to. You could potentially, maybe drill into it or, use another means to get access to that, but it would be much more difficult. Yeah, any other questions? Yeah.
You said that one of the logic was occurring in the keypad, right?
Yeah, a lot of the security logic is occurring on the keypad, that's correct.
You specifically said that it wasn't saying anything over where the pin would draw, right?
Right.
So if the pin is stored in the keypad, then how does the keypad replace it?
So can you say that last part once again?
If you replace the keypad, right, what would stop that, or what would prevent you from replacing the keypad with a different keypad?
Yeah, so you can pull off a keypad, and you're saying if you put on a new keypad, right? Yeah, there is a link message that's sent that sends basically talks with it before that it needs to link up with a certain device before the unlock commands are sent, and it won't work if you just put on another keypad. Yeah, you have to press the reset button to associate a new keypad with the device. The brute forcer was brute forcing the lock body on the back just by executing unlock commands. Yeah. Thanks. All right, that's it. Thank you very much.